Last class we discussed about transverse electromagnetic mode. Then there were some problems, so we could not progress with transverse electric mode and transverse magnetic mode. So today we will complete that portion, transverse electric mode, transverse magnetic mode. So let us start with transverse electric mode. In the transverse electric mode, the electric fields are transverse, which means electric fields are transverse to the direction of propagation. Here direction of propagation is in the z direction. Therefore we write TEZ. Z indicates that the direction of propagation is along the z direction. Since direction of propagation is in the z direction, so electric field will be in the x direction, y direction, but there will be no electric field in the z direction, which means Ez, once the z component of the electric field Ez will be equal to 0. So electric field is transverse to the direction of propagation. Direction of propagation being z, Ez is equal to 0. So what is left? Ex, Ey, Hx, Hy and Hz. These are the 5 components which can be non-zero. Maybe something is 0, but in general they will be non-zero. So Ex, Ey, Hx, Hy, Hz, these are not equal to 0. Now how to find these equations? We have already seen that if we know the longitudinal component is the component which is along the direction of propagation. So we have seen that if we know longitudinal components, then we can find out the transverse components. Transverse components are the components which are transverse to the direction of propagation, which are here Ex, Ey, Hx, Hy. Longitudinal components are Ez and Hz. Ez is equal to 0, which means if we know what is Hz, then we can find out Ex, Ey, Hx, Hy. Now what is Hz? We know Hz satisfies the Helmholtz equation. So the field away from any source, when you satisfy the Helmholtz equation, the field will be satisfying the Helmholtz equation. So del square to find out the field Hz, we have to solve the Helmholtz equation, which is del square plus k square whole is the operator. Operator is del square plus k square, that is operating on Hz. So when this operator operates on Hz, that is called to 0. So del square plus k square whole operating on Hz is equal to 0. That is the Helmholtz equation. Now for del square, you can write dou square by dou x square plus dou square by dou y square plus dou square by dou z square plus k square. And k square remains as it is. That operates on Hj, that is equal to 0. Now we have said that electric field or magnetic field in general can be represented as Fz, where F is either E or H. And we said that Fz is of the form exponential minus plus jkzz. Jkz means k subscript z, z. So fz is of the form exponential minus plus j k subscript z, z. So this implies that hz, which is a function of xyz, that is equal to h subscript z, small h subscript z, which is a function of xy, which means it contains the transverse function, transverse fields hx and hy. So that is hz. So hz, the transverse components, then the longitudinal component variation of hz is exponential minus plus j k subscript z into z. And now, if I take this one, dou square by dou z square of capital Hz, it has small hz, which is a function of xy, so that will be constant with respect to z. So what is remaining is dou square by dou z square of exponential minus plus j k subscript z into z. So when dou square by dou z square operates on this one, as you know, dou square by dou x square exponential ax is equal to a square x. So use that. If I use that, that will give me minus k square z. Already k square is there inside the operator. So therefore we'll have dou square by dou x square will remain as it is. Dou square by dou y square will remain as it is. For dou square by dou g square, we'll write minus kz, k subscript z square plus k square will remain as it is. That operating on small hz now, because hz is equal to small hz into this fact. So that will be small hz. Now let us write k square c is equal to k square minus k subscript z square. K square c is the cutoff wave number. So k square c, once we define that in this manner, then this differential equation becomes dou square by dou x square plus dou square by dou y square operating on small h subscript z, which is a function of x and y only. Z we have already taken care of. That is equal to minus k square c, and everything we have taken on to the right hand side. The k square part is taken to the right hand side. So minus k square c hz xy. So this is the differential equation that we have to solve. Now let us change the notations. Instead of hz, let us write psi xy. Instead of small hz xy, let us write psi xy. Similarly, instead of minus k square c, let us write lambda. Then this equation becomes dou square by dou x square plus dou square by dou y square operating on psi xy is equal to lambda into psi xy. This equation, you know, is a eigenvalue equation, and or eigen. In that, psi is called the eigenfunction, lambda is called the eigenvalues. So this becomes ultimately this becomes an eigenvalue problem. So you have to solve this depending on the waveguide that we are using. Now this is the general equation. We'll consider the particular case when we study rectangular waveguide and circular waveguide. Here let us consider only the general case. So we'll not solve this equation right now. We'll say that this is the equation that is required to be solved. Now, on to solve this equation, when you are going to solve this equation, what you need to do is you use the boundary conditions to find out the exact solution. Now, for PEC boundary, PEC means perfect electric conductor. And the waveguide is a hollow cylinder of perfect electric conductor. So, inside the cylinder, on the boundary, inside boundary, we have the boundary is perfect electric conductor. Now you know from boundary condition, for perfect electric conductor, there will always be a solution to the eigenvalue problem. So always a solution exists to the eigenvalue problem if we have a perfect electric conductor, and the solution gives you the modes. So TEZ modes exist inside the waveguide because there always exists a solution. So there always exists a mode. So TEZ modes exist inside the waveguide. Now what will the boundary condition? The boundary condition here is on the electric wall, perfect electric wall, E is 0. E is 0 here, Ez is equal to 0. So we will say E is 0 means dou Hz by dou N. N is the normal to the surface, normal to the boundary. So dou H by dou N is equal to 0. This is called the Neumann boundary condition. This C shows the contour enclosing the boundary. So boundary is represented by C. Within C, we have epsilon C, that is the dielectric filling the waveguide. So we take epsilon C takes care of everything, that is the dielectric constant, magnetic constant, or permittivity, permeability, as well as the conductivity. So everything is taken care of by epsilon C that we have already discussed. So this is the Neumann boundary condition, dou Hz by dou n, dou by dou n operating on Hz is equal to 0. That is called Neumann boundary condition. Neumann boundary condition, what is Neumann boundary condition? If you want to know what is Neumann boundary condition, remember that at the boundary, if you take the differentiation of a quantity of the field with respect to normal to the boundary, differentiation of the field with respect to normal to the boundary is equal to 0. That gives you the Neumann boundary condition. And as you know, from H, you can find out E by differentiating H, because you know del cross H is related to E. So from that relation, we know by differentiating H, because del cross is a differential operator, from Maxwell's equation, we know by differentiating H, we can find out E, and E is 0. So dou H by and dou N is equal to 0 here. Now, Hz shall give the solution for Hx, Ex, Hy, and Ey. So these are the solutions. Now, what we have done is we have already found out what is the expression for Hx. Hx is represented in terms of Ez and Hz. Ez is equal to 0, therefore it will be expressed in terms of Hz only. Similarly for Ex, Hy, and Ey, because Ez is 0, right hand side will contain only terms in Hz. Now Hx is dou Hz by dou x into minus plus jkz by kc square. Ex is equal to minus j omega mu by kc square dou Hz by dou y. Then Hy is equal to minus plus jkz by kc square dou Hz by dou y. Remember that Hx and Hy are dou Hz by dou x or dou Hz by dou y, and their constant is minus plus jkz by kc square. Similarly, Ex and Ey, Ex is dou Hz by dou y, Ey is dou Hz by dou x. Just reverses. X becomes y in the differentiation, y becomes x in the differentiation. And constant is minus j omega mu by kc square or plus j omega mu by kc square. Ex is minus j omega mu by kc square. Ey is j omega mu by kc square. Now, suppose the wave is propagating in the z direction. If wave is propagating in the z direction, there can be two conditions. Either Ex field and Hy field exist because of the uh, pointing vector. E cross H gives you the direction of propagation. So Ex is positive, Hy is positive, that gives you the direction Z. Or Ey is positive, Hx is negative, or Ey is negative, Hx is positive. That also gives you the Z direction, because Ey cross minus Hx is equal to Z, or Y cross minus X is equal to Z, or X cross minus Y is equal to Z. So that gives you the Z direction. Accordingly, you will get Ex by Hy, that will be same as minus Ey by Hx. Just since we have found out expressions for Ex, Hy, Ey, Hx, just take the ratio Ex by Hy. Now Ex has differentiation dou Hz by dou y. Hy has differentiation dou Hz by dou y. They will cancel out. Then minus j omega mu by kc square divided by minus plus jkz by kc square. Kc square will cancel out. J will cancel out. And since we are taking the positive direction, so minus will be taken, imply minus plus, minus will be taken, minus will cancel out. Ultimately, you will be left with omega mu by kz. Similarly, if the wave is propagating in the minus z direction, then it will be x cross minus y gives you the minus z direction. So minus ex by hy, or y cross minus x gives you the minus z. Therefore, it will be minus ex by hy. The ratio will be minus ex by hy, which will be equal to ey by hx. Y cross x gives you the minus z direction. Therefore, ey by hx, that will be again omega mu by kz. Therefore, in both the directions, whether you go by in the positive z direction or you go in the negative z direction, the ratio of the electric field component to the magnetic field component corresponding magnetic field component gives you omega mu by kz. So that omega mu by kz, since it is ratio of electric field to magnetic field, it is called the wave impedance, and it is for TE mode or TE waves. Therefore, it is called TE wave impedance. So the TE wave impedance ZTE, Z subscript TE, is by definition equal to omega mu by kz, k and subscript g. Now this is for positive direction. Similarly, for uh, positive direction, we can write ET. ET is the transverse electric field. ET is equal to x cap X component of electric field plus y cap x component of electric field. Only the xy component, only xy dependence. Z dependence is not taken here because we know what is the Z dependence. We have assumed it to be of the form minus plus j k subscript z into z. So that is known, so that will leave out. So the remaining will be this. Now remember one thing. Ex will be equal to ZTEHY. From where you get Ex is equal to ZTEHY? Since we have found out ZTE, ZTE is equal to Ex by Hy, that we know. Capital Ex by capital Hy. Now capital Ex is equal to small ex into exponential minus plus jkz, jk subscript z into z. Similarly, a capital Hy is equal to small hy into exponential minus plus jk, so subscript z into z. So this part exponential part cancels out. So capital Ex by capital Hy is equal to small ex by small hy. Just give me a moment. My power has gone up. Okay. So that is called to small ex by small uh, hy. So small ex by small hy is equal to zte, from which you can say small ex is equal to zte into hy. Similarly, you can write in the same similar fashion, we can write ex is equal to, sorry, small ey, small hy, small hy is equal to zte into uh, ex, small ex. So ultimately, you find out expression for small ex in terms of hy and zte, and expression for small ey in terms of zte and hx. So these two we have found out. What will be the expressions? Then let us find out what is z cap cross Et. Z cap is the direction of propagation, Et is the transverse electric field. So z cap cross Et, that will be equal to, since z cap is in the z direction but Et is in the x direction or y direction, it has x and y. So z cap cross x is equal to on the y cap. So y cap Ex, then z cap cross y is equal to minus x cap. So therefore minus x cap Ey. So z cap cross Et is equal to y cap Ex minus x cap Ey. That implies that z cap cross Et is equal to ZTE, let me take common, then y cap Hy, because Ex is equal to ZTE Hy, so y cap Hy, then plus x cap Hx, because Ey is equal to minus ZTE Hx, so minus, if I take minus Ey is equal to plus ZTE Hx, so from that you get plus, so ZTE whole into y cap Hy plus x cap Hx. So that I can write as y cap x cap Hx plus y cap Hy. That is the transverse component of electric magnetic field. So Ht. So therefore z cap z cap cross Et is equal to z subscript Te into Ht. So from that you can write Ht is equal to 1 by Zte into Z cap cross Et. So similarly for negative direction we will get Ht is equal to 1 by Zte into minus Z cap cross Et. So these are the two things that we will get. So then we will come to transverse uh, electric field. This is not Tm, this is Tej. Transverse electric waves. Sorry, transverse magnetic waves. Transverse electric waves we have considered. Now let us consider the transverse magnetic wave. So this is the same as the previous case, except here the electric field is longitudinal, magnetic field is transverse. Since magnetic field is transverse, therefore Hz is equal to 0. There is no component of the magnetic field along the z direction. Therefore Hz is equal to 0. If Hz is equal to 0, the remaining 5 components are Ex, Ey, Hx, Hy, Ez. These are not equal to 0. In general, these are not equal to 0. The solution that we will try to find out for Helmholtz equation is the Helmholtz equation in E. So this will be del square plus k square capital Ez is equal to 0. And now on that you can write as dou square by dou x square plus dou square by dou y square plus dou square by dou g square plus k square operating on whole thing operating on Ez is equal to 0. Now on dou square by dou z square, when it operates on Ez, Ez is equal to uh, small ez xy, that is the dependency of ez on xy. So small ez xy into dependence on z. Independence on z is exponential minus plus j k z k subscript z into z. So if I take dou square by dou z square, that will give me minus k square. That will be equivalent to minus k square z. So putting that and using k square c is equal to, is by definition defining that as k square minus kg square, the differential equation becomes dou square by dou x square plus dou square by dou y square, whole thing operating on small ez, uh, which is a function of xy, that will be equal to minus k square c operating on small ez, which is a function of xy. So this is the equation that we have to solve. Again, change the notation as in the previous case. Here, Ez should be equal to psi xy and minus k square c will be equal to lambda. So, minus k square c is equal to lambda is the eigenvalue. Ez is equal to psi is the eigenfunction. Now, here the boundary condition is Ez is equal to 0, because on the on a perfect conductor, electric field is 0 on the surface of a perfect conductor. Electric field is 0. We are solving it for electric field. This equation we are solving for electric field. Therefore, Ez will be equal to 0. If the field is equal to 0 on the boundary, then the boundary condition is called the Dirichlet boundary condition. So that we will use the Dirichlet boundary condition for solving this equation when we solve this equation for a rectangular waveguide or a circular waveguide. So here it is the Dirichlet boundary condition Ez is equal to 0. Then we'll proceed as in the previous case. Ex, Hx, Ey, Hy, these are functions of Ez only. That is, they are not functions of Hz. And these functions are Ex is equal to minus plus jkz by k square c, and then dou E z by dou x. Similarly, Hx is equal to j omega epsilon c by k square c dou Ez by dou y. Py is equal to minus plus jkz by kc square dou Ez by dou y. Hy is equal to minus j omega epsilon c by k square c dou Ez by dou x. Now, these are the expressions for Ex, Hx, Ey, and Hy. Now here you can see minus plus sign. Minus indicates the wave is propagating in plus direction. Plus indicates the wave is propagating in minus z direction. Now when the wave is propagating in positive direction, positive z direction, as in the previous case, we get Ex by Hy, that is equal to minus Ey by Hx, that will be equal to, in this case, Kz by omega epsilon c. When the wave is propagating in negative z direction, this will change. This will become minus Ex by Hy, that is equal to Ey by Hx. That will be again Kz by omega epsilon c. Since we are taking ratio of electric to magnetic field, and this ratio will be the wave impedance, and this is the uh, TM wave. Therefore, we'll call it TM wave impedance, not TE wave impedance. This is TM wave impedance. TM wave impedance is and ZTM, that is called to Kz by omega epsilon c. This is by definition. Here again for positive direction we have ET. ET is the transverse electric field, uh, except the Z variation. ET, considering the variation in x and y, so ETXY will be x cap EX plus y cap EY. Now, again, here you can see that capital Ex by Hy is same as small ex by small hy. Capital Ey by capital Hx is same as small ey by small hx, because exponential uh, minus plus j kz into z, that will cancel out in the numerator and denominator, leaving out the small e and small h. Okay. So using that, we can now write a small ex is equal to ztm hy, and small ey is equal to minus ztm hy. So minus small t minus ztm small hx. Now, again, as in the last slide, here what we will do is we will take z cap cross et. So z cap cross et is equal to y cap ex, because z cap cross ex is y cap. So y cap ex minus z cap cross z cap cross y cap is equal to minus x cap. So this will give you y cap ex minus x cap ey. So that implies that z cap cross et is equal to ztm whole into operating into y cap into ex is hy plus h cap into hx. Plus comes from this part, since ey is equal to minus ztm hx. So if I put minus ey, that is plus ztm hx. So from that this plus comes. So z cap et is equal to ztm whole into y cap hy plus x cap hx. So that is equal to ztm into ht. So from that we can find out ht is equal to 1 by zte whole into z cap cross et. Similarly, for the negative direction, ht is equal to 1 by ztm into minus z cap et. So with that, we come to the end of TE and TEM mode. So we have discussed about the introduction of waveguide. In this discussion, what we have done is we have discussed what is TEM mode, what is TE mode, what is TM mode, and for TE mode, TM mode, and TEM mode, we have found out what are the wave impedances. Then we have found out a relationship between wave impedance and the